The aim of this paper is to show, using the example of the benzene model, the importance of magnetic fields of elementary particles and their vectors of magnetic moments, in the construction and analysis of models of the structures of atoms and molecules, and their bonds with other atoms, ions and molecules. Magnetic fields of elementary particles are among the basic physical properties. Unfortunately, quantum mechanics completely ignores this phenomenon when describing the resulting state of models of atoms and molecules. The structure of the benzene molecule was determined by electron diffraction in 1929. Spectroscopic measurements show that the benzene molecule is a planar hexagon and that all its carbon-carbon bonds have the same length of 140 picometers. The planar configuration and the angle of 120 degrees is justified in the current literature by the properties of the hybridized sp2 double bond. Current theories propose the possibility that electrons in benzene are localized with a probability distribution throughout the nucleus of the molecule. However, none of the schematic representations used explicitly depicts the distribution of elementary particles and their interaction in the benzene molecule. An older notation of the schematic representation of benzene is a regular hexagon. If the structure of benzene exactly matches this scheme, 3 of the bonds between the carbon atoms would have to have the properties of a single bond and the remaining 3 would have the properties of a double bond. This would be reflected, for example, in the lengths of the bonds. The shape of the benzene molecule in such a case would have to be approximately as follows, where the numbers indicate the length of the bond in picometers. However, experimentally it has been found that all 6 bonds between carbon atoms in the benzene molecule have the same length of 140 pictometers. It follows that the notation of the molecule does not describe the actually determined structure of benzene. The introduction of mathematically constructed hybridization of electrons of the carbon atom in quantum mechanics does not allow us to explain the differences in length between a single bond, a double bond, or a bond in a benzene ring. Only if we preserve the physical nature of the energies of the electrons of the carbon atom are we able not only to explain these differences, but also to analyze them. The model, based on the solution of the Schrödinger equation, completely neglects the existence of the magnetic field of the modeled elementary particles, their magnetic moments and their mutual magnetic interaction. However, this seemingly negligible shortcoming is then manifested both in the final construction of the model, its analysis and solution of the structure of the benzene molecule, as well as in the subsequent calculated distances and energies of bonds with other molecules. When constructing the structure of the benzene molecule as a deterministic model, we should start from the basic structure of the carbon atom. It is not a mathematically invented hybridized structure, but a model capturing the physical nature of a carbon atom with 2 electrons of type 1s 2, 2 electrons of type 2s 2 and 2 electrons of type 2p2. Which are energetically different and are experimentally documented on the basis of measured values of spectral lines. The electrons in the carbon atom model do not form a regular tetrahedral structure, as is the case with the CH4 methane molecule model, because the different energies of the electrons of the 2s and 2p of the carbon atom result in different distances of these electrons from the nucleus of the atom. The spatial distribution of their electrons is determined by the structure of the nucleus of the atom. In the model of the carbon atom according to the ring theory, the magnetic moments of the protons of the nucleus, and the magnetic moments of the electrons, play a key role. However, in the benzene molecule model, the carbon atom does not retain its original structure, but the spatial distribution of its electrons changes. This is due to the fact that after the formation of covalent bonds with 2 adjacent carbon atoms and 1 hydrogen atom, 3 pairs of bonded electrons are formed, against 1 non-bonding excited electron. The double negative charge creates a repulsive force that flattens pairs of bonding electrons into a plane in the center of which lies the nucleus of the carbon atom. The non-bonding excited electron is held by their repulsive force above the center of the atom. This structure of the trigonal pyramid will form the basis for the formation of the planar benzene molecule. According to the ring theory, models of carbon atoms allow the formation of several types of simple covalent bonds. This is made possible by the 2 types of electrons 2s and 2p and the 2 types of globules in the nucleus of the atom model with opposite directions of the magnetic moment vectors of the protons. In the benzene molecule model, the covalent bond is formed by 1 2s type electron of one carbon atom and 1 2p type electron of the other carbon atom. The carbon atoms are rotated in such a way that the direction of the magnetic moment vector of the proton globule of the C1 atom, directed outwards from the globule, follows the parallel direction of the magnetic moment vector of the proton globule of the nucleus of the C2 atom, which is directed inwards of the globule. The model of the benzene molecule shows that neighboring bonded hydrogen atoms, or other atoms or groups, always have the opposite external magnetic moment vector when bonded with the carbon atom. However, all of them are bound to electrons of the 2p type of carbon atom, and hence the hydrogen bonds of benzene are equivalent. The bond length of CH is 109 picometers. The experimental demonstration of the model situation of equivalence of CH bonds is the only discontinuous signal in the benzene spectrum in NMR measurements. Demonstration of the structure of a benzene molecule model. Looking sideways at the diagram of the structure of the benzene molecule, we can see that the three free non-bonding electrons 2p at the top of the molecule model have an opposite external magnetic moment vector to the nucleus of the carbon atom than the three non-bonding electrons at the bottom of the molecule. This means that the magnetic moment vectors of all 6 non-bonding electrons are parallel, and together they create the magnetic field of the entire molecule. According to the models of the ring theory, the type of single bond between electrons of type 2's 2p carbon atoms is applied, for example, to aromatic compounds and conjugated double bonds. Using the proposed models and approaches in the works of ring theory, we can calculate the bond length and binding energy of this bond in the benzene molecule. The enumerated values of radius and current for electrons 2p and 2s are used to calculate dynamic equilibrium electric and magnetic forces. The sum of the distances after enumeration from the equations for electric and magnetic force in the axis of the rings of protons and electrons is 140 picometers, which is in accordance with the experimentally determined value. For the purposes of calculating electron radii, bond length, and binding energy, we use all the equations that we have used for the calculations of the hydrogen atom. According to experiments, both the electron and the proton have their magnetic field and their magnetic moment. The value of these magnetic moments is given in the NIST database of constants. The magnetic moment of the electron is almost 3 orders of magnitude greater than that of the proton, and therefore it is the dominant source of the magnetic field, which affects the magnetic field of the entire molecule and affects its structure as well as the bond between the benzene molecule and other molecules. The figure shows schematically the magnetic fields of valence electron pairs, which are entangled with adjacent magnetic fields due to the parallel direction of the magnetic moments. These entangled magnetic fields create a force of attraction that counteracts the repulsive force of the electrons' electric fields. In this diagram, we can see the overall interconnectedness of the magnetic fields of atoms and individual elementary particles in the benzene molecule. Unfortunately, quantum mechanics, presented by the Schrödinger equation, does not take into account magnetic energy and magnetic field interactions between individual elementary particles. However, for the purposes of chemistry, explanation of bonds, and structures of atoms and molecules, the existence of these interactions is irreplaceable. Looking sideways at the model of the benzene molecule, we can see the entanglement of the magnetic fields of the non-bonding electrons at the top and bottom of the molecule with the bonding electrons of the covalent bond between the carbon atoms. All of these entangled magnetic fields have an effect on the total magnetic moment of the benzene molecule. The magnetic fields, made up of the 6 free electrons in the model of the structure of the benzene molecule, can produce a resultant strong magnetic field superimposed at the center of the hexagonal molecule due to parallel magnetic moments. This magnetic field creates a virtual magnetic moment at the center of the hexagon, the vector of which is anti-parallel to the vectors of magnetic moments of free electrons. The radius of the molecule represents the radius of the virtual magnetic dipole of the benzene molecule. These magnetic fields can explain the aromatic interactions of benzene in non-covalent bonds with cations and anions, or the bonds of the benzene dimer. The magnetic fields produced by the electrons of the benzene molecule model may also explain the possibility of a relatively strong hydrogen bond between the water molecules and the benzene molecule. The proton acceptor is the free non-bonding electrons of the benzene molecule. The virtual magnetic moment at the center of the hexagon of the molecule has an anti-parallel orientation with respect to the magnetic moment vector of the proton of the hydrogen atom in the water molecule, and therefore creates a repulsive force against the magnetic field of the hydrogen atom proton. The repulsive magnetic force of the hydrogen atom proton against the magnetic moment of the benzene molecule maintains a dynamic equilibrium between the electric force of attraction between the proton of the hydrogen atom in the water molecule and the non-bonding electrons of the benzene molecule. The importance of magnetic fields will be demonstrated on the example of the folding of some types of benzene dimer, which is referred to in the scientific literature as pi folding. 3 types of benzene dimers are reported in published works: sandwich, parallel shifted and T-shaped. In order to understand their bonds and the subsequent possibility of calculating distances and binding energies, we will use a schematic representation of models of benzene dimers according to the ring theory in the following text. To explain the equilibrium state of the bond between the electrons of 2 benzene molecules or the bonds with other atoms, ions or molecules, we cannot do with the electric forces of their electric fields alone. According to the ring theory, the dynamic equilibrium distance between the 2 electrons of the 2p in the benzene dimer is determined by the equilibrium between their repulsive electrical force and the electric force of attraction between the proton of the carbon atom in the benzene molecule and the non-bonding electron of the 2p carbon atom in the other benzene molecule, and the magnetic force of attraction between the rings of the 2 electrons on the common axis. The distance d2 is obtained from the equations for the equilibrium state between the electric and magnetic force between the 2 non-bonding electrons 2p in benzene molecules. After substituting the known constants and calculated values, we get the dynamic equilibrium position of the forces, and we can quantify the distance between the 2 electrons of the 2p benzene dimer. The total quantification of the distance d0 is consistent with the highly accurate value given in the tables of calculations for the potential energy surface of the benzene dimer. For the S-type benzene dimer, the same distance d2 is between the trio of 2 non-bonding electrons 2p in benzene molecules. The distance d2 is obtained from the equations for the equilibrium state between the electric and magnetic force between the trio of 2 non-bonding electrons 2p in benzene molecules. The total distance d0 is consistent with the highly accurately calculated value given in the calculation tables for the potential energy surface of the benzene dimer. As the distance increases, the binding energy between the dimers decreases, and hence the S-type benzene dimer with the lowest binding energy is the least stable. In the case of a TS-type benzene dimer, the solution of bonding, distances and binding energies is the same as that of hydrogen bonding of benzene with water. The virtual magnetic moment at the center of the benzene molecule is opposite to the magnetic moment of the proton of the hydrogen atom and therefore exerts a repulsive force on each other. The electrostatic force exerts a force of attraction between them. The distance d2 is obtained from the equations for the equilibrium state between the electric and magnetic force between the non-bonding electrons 2p in the benzene molecule and the proton of the hydrogen atom in the second benzene molecule. According to our calculations, the total distance d0 between the centers of the benzene dimer molecules of the TS type is in accordance with the highly precisely quantified value given in the tables of calculations for the potential energy surface of the benzene dimer. For the bond between benzene and lithium cation, the dynamic equilibrium distance is given by the equilibrium between the electric force of attraction between the protons of the lithium-ion nucleus and the free electrons of benzene, the electric force repellent between the protons of the lithium-ion nucleus and the protons of the carbon atom in the benzene molecule, and the magnetic force repellent between the magnetic moment of the benzene molecule and the magnetic moment of the lithium-ion nucleus proton, all in the axis of the benzene molecule. After substituting the known constants and enumerating the values, we can quantify the distance d2 between the electrons of 2p benzene and the proton of the lithium-ion nucleus. The total quantified distance d0 between the benzene ring and the lithium cation is consistent with the experimentally determined value of the distance between the benzene and lithium-ion complex. In the case of benzene bonding with anions, the role of the magnetic field is opposite to that of bonding with cations. Since the magnetic moment vectors of benzene and electron of the anion fluorine are parallel, the strength of the magnetic fields is attractive. The dynamic equilibrium distance d2 is then given by the equilibrium between the electric force of the repulsion between the electron of the anion of fluorine and the 3 electrons of benzene, and the electric force of attraction between the electron of the anion of the fluorine anion and the protons of the carbon atom in the benzene molecule, and the magnetic force of attraction between the magnetic moment of the benzene molecule and the magnetic moment of the anion of fluorine, all in the axis of the benzene molecule. After substituting the known constants and calculated values, we get the dynamic equilibrium position of the objects affected by the forces, and we can calculate the distance d2 between the electrons of 2p benzene and the electron of the anion fluorine. The total calculated distance d0 between the benzene ring and the fluorine anion is 257 picometers. An experimentally measured value of the distance d0 for the bond between benzene and fluorine anion was not found in the available literature. The calculated value of d0 for the bond of hexafluorobenzene with the anion fluorine is 2.57 A. According to the instantaneous state and dynamic changes of the electron model, we can assume that the benzene molecule will also try to rotate its position in the external homogeneous magnetic field so that the plane of its ring is perpendicular to the direction of the external magnetic field. This is due to the structure of its 6 non-bonding electrons, which all have the same parallel direction of their magnetic moments. After the plane of the ring of the benzene molecule is rotated perpendicular to the direction of the external magnetic field, the action of the external magnetic field in the corresponding parts of the electrons, based on the ring structure, superimposes instantaneous values of the magnetic field, the resulting direction of which is opposite to the direction of the external magnetic field. This will reduce the magnetic moment in electron models that have a parallel magnetic moment with an external magnetic field. Proton models bound by the dynamic equilibrium of forces to their models of non-bonding electrons also have the plane of their ring perpendicular to the external magnetic field, but they always have the opposite direction of the magnetic moment vector. Therefore, due to the action of an external magnetic field, the magnetic moments of protons in the ring structure of protons will be amplified. The free valence electrons of the benzene molecule interact with the external magnetic field with their magnetic fields and form an uneven anisotropic magnetic field in their vicinity. The magnetic moments of the protons in the nucleus of carbon atoms in the benzene molecule are located both in the area of the action of the external magnetic field, but also in the area of the magnetic field of the electrons bound with them. These electrons create a barrier with their magnetic field, one could say, shielding the protons from the effect of the external magnetic field. However, if their magnetic moment is reduced by the induction of an external magnetic field, then the protection of protons and the shielding is reduced. By weakening this protection, the external magnetic field will affect the protons and their magnetic moments will be amplified even more. The amplification described in this way causes that in NMR techniques and measurements, protons are strongly shielded and have a relatively high frequency absorption and a larger chemical shift of delta equals 7. The aim of this paper was to show the importance of magnetic fields of deterministic approaches to the description of elementary particles and their vectors of magnetic moments in the construction and analysis of models of the structures of atoms and molecules and their bonds with other atoms, ions and molecules. Thanks to the carbon atom structure model, we were able to determine the length of the C-C bond and the CH bond in the benzene molecule model, and to show the inconsistencies and consequences of using the hybridization theory. We described and clarified the structure and properties of non-bonding pi electrons without the theory of delocalization and illustrated their magnetic fields as well as the magnetic field of the whole benzene molecule. Using the accepted magnetic fields in the model, their vectors of magnetic moments and magnetic forces, we showed examples of non-covalent bonds of benzene and its pi electrons with water molecules, cations and anions of atoms. We have discussed the possibilities of stacking benzene dimer. Magnetic fields and their energy of all elementary particles are among the basic physical properties. Quantum mechanics completely ignores this phenomenon when describing the resulting state of models of atoms and molecules. More information about the model of the benzene molecule and the ring theory can be found at www.ringtheory.eu. Thank you for your attention and keep an open mind.